Good afternoon, everyone. My name is Melissa Masbruch, and I'm a hydrologist with the USGS at the Utah Water Science Center. In this presentation, I will be looking at sources, sinks, and flow paths of surface water and groundwater within the Escalante River watershed. When we speak of a watershed, what are we talking about? The official definition of a watershed is that it includes all of the source area contributing surface water to a single defined outlet point. So for the Escalante watershed, we are speaking of the area that provides surface water to the Escalante River between its headwaters and the point where it confluences with the Colorado River at Lake Powell. The boundaries of a watershed are typically defined by hydrographic and topographic criteria. These boundaries, however, may or may not match groundwater boundaries. This figure shows a schematic of the water cycle. The ultimate source of water to surface water and groundwater is precipitation. As is shown on the figure, snowmelt and other surface runoff contribute water to streams. These are the surface water sources that are used to define the boundaries of a watershed. Groundwater may also discharge to streams. This is often referred to as base flow, and this is the water that sustains perennial streams in the summer and fall after snowmelt has ceased and between precipitation events. In the case of the Escalante watershed, most of the groundwater recharge occurs from the infiltration of snowmelt at higher altitudes near Boulder Mountain and the Aquarius Plateau. Hydrogeologic units in the Escalante watershed consist of local and regionally extensive aquifers separated or underlain by regionally extensive confining units. Aquifers are more permeable units that can store and transmit groundwater. Confining units, on the other hand, are less permeable units that impede groundwater movement. Within the Escalante watershed, there are three regionally extensive aquifers: the Mesa Verde, San Rafael, and Glen Canyon Group aquifers. These are separated from each other by three regionally extensive confining units: the Trobrick Shale, the Carmel Formation, and the Chinle-Moenkopi formations. Above the Mesa Verde aquifer, unconsolidated materials may act as a fourth local scale aquifer. Here's a map showing the hydrogeologic units at land surface. The units generally increase in age from west to east, with the exception of Boulder Mountain, the Aquarius Plateau, and the unconsolidated deposits. Groundwater recharge to the bedrock is enhanced where the bedrock is covered by unconsolidated deposits, where the bedrock is fractured, or where precipitation is high or there is slow infiltration of snowmelt, such as on the flanks of Boulder Mountain, for example. How do streams and springs form in the watershed? Streams are formed within the Escalante watershed in two ways. Either in areas where 1, the water table intersects the land surface, or 2, the stream is at the surface because it is underlain by a confining unit. Groundwater and surface water interact within streams, and this interaction results in gaining reaches and losing reaches along the stream. Gaining reaches occur where the water table intersects the land surface, and the water table is lower in altitude in the stream than it is in the surrounding subsurface or aquifer. In this case, groundwater flows into the stream from the surrounding aquifer. In losing reaches of streams, the water table may or may not intersect the land surface, and it is at a lower altitude in the surrounding subsurface than in the stream. Groundwater flows from the stream to the surrounding aquifer. The top figure shows the case where the water table intersects the land surface only at the stream bed. The lower figure shows a disconnected stream, which might occur if the stream is underlain by a confining unit. Springs form in one of two ways within the watershed. The first is where the water table intersects the land surface. In general, this occurs at high altitudes within the watershed. Examples of these types of springs are Stump Springs and Beaver Spring. The second way springs occur is where they discharge along contacts between aquifers and confining units or through fractures. These springs generally discharge along the canyon walls. Here's a photo along the river below Coyote Gulch where you can see the spring emanating from high on the canyon wall. Likewise, here is another such spring along the river just below the gulch. To better illustrate this, here is a vertical view of the hydrogeologic units where the blue arrows represent groundwater movement through the subsurface. As illustrated, water enters the aquifer and moves vertically downward until it reaches the base of the aquifer, where the underlying confining unit impedes further downward movement. The groundwater will then move laterally along the base of the aquifer until it discharges along the side of the canyon wall. The same can happen with vertical upward movement of groundwater. Or the groundwater may move laterally until it intersects a fracture, and the groundwater will move preferentially within the fracture as these are more permeable than the aquifer material. The stream will then emanate from the fracture along the canyon wall. Now, I'm going to talk a bit about studies and monitoring work the USGS has performed within the watershed. Shortly after the establishment of the Grand Staircase-Escalante National Monument, Jeff Freely of the USGS constructed a reconnaissance-level, three-dimensional groundwater flow model for the monument. This model simulated steady-state conditions and was not calibrated. The black line on the figure denotes the active model boundary in relation to the monument, which is shown in the colored areas. The model was used to simulate flow paths to the Escalante River using a particle tracking analysis routine. This figure shows the simulated paths that a particle of groundwater took within the model. The colors indicate the velocity of the groundwater flowing along these paths, with cooler colors indicating faster velocities. From the simulation, it was assumed that the Escalante River was a terminal groundwater sink for the basin, almost along the full length of the river. To investigate groundwater and surface water interaction and verify the simulated flow paths from the groundwater model, the USGS performed a seepage study along the Escalante River in October 2001. Seepage studies are usually performed in the fall during dry periods when it is assumed that any gains in the river aside from incoming tributaries are from groundwater discharge to the stream. This figure shows the results of the study. In particular, I want to call your attention to the blue arrow. The thickness of the blue arrow represents the volume of stream flow within the river, where greater thickness equals greater stream flow. This study found that there was very little stream flow gain between Boulder Creek and Coyote Gulch, as is shown on the figure, where the thickness of the arrow does not get much bigger downstream of Boulder Creek. That is, no significant groundwater gains to or losses from the river were found. Additionally, the accretion or increase in stream flow between Pine and Boulder Creeks was mainly from the inflow of tributaries to the north of the river, namely Pine, Mamie, Sand, Calf, and Boulder Creeks. By looking at the streams in relation to the hydrogeologic units, some assumptions regarding the source of water to those northern tributaries were made. First was that the source of water to those tributary channels is from the Glen Canyon Group aquifer, or more specifically from the Navajo sandstone, especially along Boulder Creek. Second was that the water gained by the tributaries from the Navajo sandstone was primarily from spring discharge along the stream channels and groundwater flowed through fractures. To date, these assumptions have not been formally investigated or ground-truthed. However, here is an image showing the fracture patterns in the Navajo sandstone between Mamie and Sand Creeks. The yellow lines are shown to highlight the orientation of the fractures in relation to the creeks. As is evident, the orientation of the fractures are relatively perpendicular to the tributary streams, indicating that groundwater could discharge into these fractures and very easily flow to the streams. Additionally, plotting the stream altitudes on the figure as shown in the red dots, we see that the groundwater flow through these fractures is likely from the upper left to the lower right, or roughly from the northwest to the southeast. Basically, the fractures act as conduits of groundwater flow, and direction of that flow is ultimately towards Boulder Creek. Moving on to other USGS monitoring activities within the watershed, the USGS collects data at two active stream gauges. The first is Escalante River near Escalante. This gauge has daily mean discharge records from 1911 to present. However, it does have a couple of large data gaps within that period. This gauge also has instantaneous discharge records from 2007 to present and this hydrograph shows data for water years 2015 through 2023. On this hydrograph, it is easy to see the annual snowmelt signal in early spring, followed by the flashier monsoonal event signals during the summer of each year. The second active gauge is Pine Creek near Escalante. This gauge has daily mean discharge records from 1950 to present, with a small gap of only a couple of years in the mid-1950s. It also has instantaneous discharge records from 2007 to present, and this hydrograph shows the data for water years 2015 through 2023. At this gauge, the snowmelt peak is shifted later in the spring versus the Escalante River gauge, and it's not as easy to distinguish the monsoonal events from the snowmelt peak. The USGS has also been monitoring groundwater levels at 3 wells within the watershed since about 1980. The hydrographs I will present here are for annual springtime water levels between 1993 and 2023. The 2 wells near Boulder are between 400 and 500 feet deep and are completed in the Navajo sandstone. Both of these wells show a steady decline in water levels of about 12 feet over this 30-year period. This groundwater decline could be caused by human impacts from pumping, climate variability, or a combination of the two. The 3rd well is located near Escalante, and unfortunately, no information is available as to what depth or unit the well is completed in. While water levels in this well fluctuate up to 3 feet from year to year, water levels at this well do not show the same long-term decline as the wells near Boulder. Given the shallowness of the water levels and their somewhat flashy nature, it is likely that the well is completed at a much shallower depth and possibly in a different unit than the wells near Boulder. Water levels in this well are likely more responsive to climatic impacts. The utility of data collection and interpretations helps us to more fully understand how water moves through the system and the amounts of water in the system. Data from streamflow gauging stations and seepage studies exhibits the integrated effects of physical, biological, and hydrologic characteristics of a drainage basin or subbasin. This data can also be used to quantify surface water and groundwater flux. Spring inventories and classification data can be used to identify the location and amount of groundwater discharge and to identify the source of water to the springs. Groundwater levels can be used to indicate impacts of groundwater withdrawals or other changes on the groundwater reservoir. Finally, watershed and groundwater flow models can be used to synthesize existing hydrologic data, improve the conceptual understanding of the system, simulate interactions between different components of the system, and as a tool for investigating potential future impacts from changes in climate or human use. Thank you.